Hi, in this video, we want to take a look at matrix algebra. All right, so a matrix is a rectangular table of numbers. So there's a number of rows and a number of columns. And we're not thinking about the movie, and we're not Keanu Reeves. You can go watch that if you want. I didn't see much math in that movie, unfortunately. Now, a matrix, if we look at abstract algebra, a matrix can be a lot more complicated. For us, it's a table of numbers and that's it. We're not going to get into fields or anything more complicated. It's just rectangular table of numbers. So let's look at this example. I have A is the matrix 1, 2, 3, 4, 5, 6. It's got 3 rows and 2 columns. So remember, if I look at architecture, columns go up and down. So columns on a matrix go up and down also. And the rows are just perpendicular. This is a 3 by 2 matrix. So when we have a data matrix, each observation corresponds to a row, and each column corresponds to a variable. That's how we organize our data that way. And that way, if you hand me data, even if it's not labeled what the rows and the columns are, I can know, hey, that this entire row is the observations, this entire column is a variable. Now, the dimensions of a matrix, it always goes rows before columns. So if we look back at A moment ago, we can see that we have 1, 2, 3 rows and 2 columns. Rows before columns, it's a 3 by 2 matrix. So you'll hear the dimension of it is just 3 by 2. Now, for our notation, something that we're going to do is that we're going to say that a capital letter is a matrix. And so that represents an entire table with a bunch of different numbers on there. Lowercase letters represent the entries on the matrix. Now the subscripts indicate rows and columns. So let's take a look at an example. Capital A, this is a matrix. And from the previous example, this is the matrix it is. 1, 2, 3, 4, 5, 6. Now you'll notice that as I list these items, I go column by column. So it's like we're going variable by variable in our minds. That's a standard way of thinking about matrices, is that we think of them as being like a vertical. Like a vector is a vertical item. Now another way to denote this is I put parentheses around lowercase a subscript ij. All right, so the parentheses says, hey, I'm representing all of these entries on the matrix. So the parentheses says, I'm trying to represent everything here. The subscript says these are the entries, and sorry, the lowercase letter says it's the entry of the matrix, and then the I tells you the row, the J tells you the column. So for example, if we look at A sub 2, 1, this is second row, first column. But look over here, second row, first column is going to be 2. Oh, and when we say rows, we go from top to bottom. When we say columns, we go left to right. So you'll notice A3, 2, third row, second column is 6. Third row, 1, 2, 3, second column, 1, 2. I'm in this position. Now, a vector is a matrix with 1 column. And when I say vector, I'm going to be saying it's going to be vertical. Now, if you just say vector by itself, knowing nothing further special about it, it's automatically vertical. Now, sometimes you'll hear me say column vector, just to emphasize that it's vertical in our alignments. And then a row vector is horizontal. And if we start working with like stochastic processes, we'll be using row vectors more than elsewhere in the course. So if you hear row vector, it's horizontal, column vector is vertical. If you hear just vector, we represent it vertically. Now, in matrix algebra, the word transpose is different than transpose in SAS. The transpose operator, or proc transpose in SAS does the mathematical transpose, but it also does a lot more. Like the mathematical transpose is just the beginning of what proc transpose can do. So just know that there's a difference. So transpose is where we take the matrix and all the rows become the columns, all the columns become the rows. Now there's two major ways to denote this. Either a little dash right there up at the top, little apostrophe, or a T up top, the right-hand side. Those are the two major ways. I prefer the T because that emphasizes what it is, because T for transpose. The textbook uses the apostrophe. So you're going to need to be flexible on this one. All right, so remember that when we looked at A previously, we had 1, 2, 3, 4, 5, 6. So the first column was 1, 2, 3. Well, when I take the transpose, the first row is 1, 2, 3. When I had regular A, the second column was 4, 5, 6. Well, when I take the transpose, the second row is 4, 5, 6. Okay, so that is just how the transpose works. It just basically takes the same data and just rearranges it into another format. And this will be a very important operation in this class for linear models. Now, another way to represent this. So remember I said rows become columns, columns become rows. The transpose operator, and we can think of this as a function, the transpose operator takes the rows and makes them into columns, makes the columns into rows. So the subscript ij becomes ji. It just switches. Rows become columns, columns become rows. Okay, well, the transpose has a lot of like really neat, slick properties. So let's take a look at a few of them. The transpose of the transpose is the original matrix. So if you think about it, the rows become the columns, and then here the columns become the rows, so it undoes it. Here, inside, the columns become the rows, then the rows become the columns, so having it twice undoes it. That's a self-inverse function. Now, if I take A plus B, and then I take the transpose of the whole thing, that's the same as transpose A plus transpose B. It respects addition. Now, here's one that might surprise you. If I take the transpose of A times B, and we haven't talked about matrix multiplication yet, but this is an important one, and this will come up later down the road. The transpose of A multiplication B, the whole thing, is equal to the transpose of B times the transpose of A. You can see that the order became switched. Now, we haven't talked about matrix inverses, but here's an important property that will come up later. If I take the transpose of an inverse, same as the inverse, sorry, it's the same as the transpose, then you take the inverse. You know, we can see that the operations just switch order. The operations are commutative with each other. And if we have scalar multiplication, if we take scalar multiplication times A, transpose, that's the same as the scalar being multiplied by A transpose here. And a lot of these operations, we honestly won't even talk about until the next video, but I want you just to see these and just kind of keep it in the back of your mind that there's special properties on the transpose for later down the road. And something we have not talked about yet is the determinant, but I'm going to go ahead and slap this down now. The determinant of the transpose of the matrix is the same as the determinant of the matrix if A is a square matrix. And one that is going to come up over and over in this class is that there's the transpose of A times A and A times the transpose of itself are going to be positive semi-definite matrices as long as all the entries on the matrix are real numbers. Okay, why do I have to say this? Well, if we're dealing with complex numbers, then it's not going to be positive semi-definite because there's just going to be a little bit more. It'll be it's almost correct. We have to just change that symbol a little bit. But in this class, we're really not going to be worrying about complex entries except for maybe eigenvalues, and that's not going to come up that much for us. So we're going to be keeping it real, yo. Now, another thing we have not talked about is eigenvalues, but it's super important, so I want to talk about it early to get so that it gets here in your head. The eigenvalues of the transpose of a matrix equal the eigenvalues of the matrix itself, as long as A is square. And something about the dimensions, if A is an n by P matrix, then A transpose is P by n. And so remember, this is the dimension. This is number of rows, number of columns. When I switch it, this P becomes the number of rows and n becomes the number of columns. And a single number that is not on a matrix is just called a scalar. Technically, a 1-by-1 matrix is different from a scalar. One thing that you'll notice when you work with software, though, MATLAB is probably the best example of this. I believe R does it also, is that it will treat a 1-by-1 matrix as a regular number. And that makes sense for software, but if we're doing theoretical mathematics, it doesn't really make as much sense. Now, matrix equality, two matrices are equal to each other if and only if every entry in corresponding positions are equal to each other. So for each row and column combination, the entries have to equal each other. So what I'm saying here is upside down A is for all ij. So for all entries on the matrix, so every row, every column combination, if the entries are equal to each other on the two matrices, then the entire matrix, so the entire matrices are equal to each other. So if I go through, 1 equals 1, 2 equals 2, same position, 3 equals 3, same position, 4 equals 4, same position, 5 equals 5, same position, 6 equals 6, same position. Okay, now something about this. The only way that this aspect, this all ij aspect, can be satisfied is if the two matrices are of the same dimensions. If they're not, if they have different dimensions, it's automatically not equal to each other. All right, so if I look here, 1 equals 1, 2 equals 2, same position, 3 equals 3, same position, 4 equals 4, same position, 5 equals 5, same position, 6 does not equal 7. One entry on there changed it so that it's, these two matrices are not equal to each other. One little difference means they're not equal. Now here, even though I've got 1, 2, 4, 5 on the left-hand, left-hand two columns of both of these matrices, these are not equal to each other because they have different dimensions. I'm missing a column over here. Therefore, these are not equal. All right, so now let's take a look at a proof, and this is a really easy theorem. If A is a matrix, then the transpose of A, transpose, is equal to A. So what we're saying is that if I take the transpose twice, I get the original matrix back, self-inverse. Okay, so how are we going to work this out? I'm going to have to go by the definition of transpose, definition of a matrix. So A, let's say that's equal to lowercase a, ij. If I take the transpose of the matrix, then all that does is that changes the order on the subscripts, right? I and j switch, rows become columns, columns become rows. Okay, so we know that A transpose is equal to A sub ji in this notation aspect. Okay, well, what happens if I take the transpose of both sides of this equation? Well, A transpose transpose is equal to this. Well, what did the T do a moment ago? The transpose operator switched the subscripts. Well, it switched the subscripts, so boom, it switches again. So therefore, we can see that A transpose transpose is equal to the original matrix. Now, when we're done with a proof, the author of the textbook and myself like to put a little box by there. Some people like to put a QED. It's called a Helmholtz box after the mathematician. I believe he was at Indiana University, but it's called a Helmholtz box right there. And that signals that we're done with the proof. It's complete. It's over. A matrix such that A transpose is equal to A is called a symmetric matrix. So if you think about that, one of the things that has to come out is that the number of rows has to equal the number of columns for this to be possible. So all symmetric matrices are square, but not all square matrices are symmetric. Now, a diagonal matrix, or the diagonal of a matrix is all the entries where the j equals the I in the subscript. So the diagonal of a matrix is A11, A22, A33, A44, A55, and so on. Now, why do we care about this? These are going to be heavy hitter entries when it comes to a lot of the special values that arise from matrices, specifically eigenvalues. All right, so here's an example. The diagonal of 1, 2, 3, 4, 5, 6 is just going to be 1, 5. You can see that A11 and A22 is 1, 5. 1, 5, like that. Now, one thing you'll notice is that I've got 2 rows and 3 columns, so I need the subscripts to match, so I stop at 2 when I talk about a diagonal. Now, unfortunately, in mathematics, we overuse terms. If you go into education, you go into psychology, something like is slightly different, and they try to make a whole new terminology and phrase, and they make a whole new dictionary out of every single concept, and they never want to use like the same word twice. Mathematics is a polar opposite. What we do, we reuse words over and over and over. We use the same word for a similar concept, or maybe a completely different concept, and you have to know from context what it's meaning. So when we say diagonal, there's 2 meanings in this class. One is when I say the diagonal of a matrix, it could be the entries along what's called the diagonal, or it could be a matrix where we put 0 everywhere but that diagonal. And here is the example over here. And so you'll have to know from context what's going on. Do I want just like a string of entries, or do I want a matrix from context? And unfortunately in mathematics, we just have to suck it up and figure this out. You know, this is like one of the things that will trip up a lot of students from not knowing that the context for the word, you know, really matters. Now, another important concept is a diagonal matrix. So here, this is the diagonal of the matrix, is what we're referring to here, the diagonal of the matrix. Down here, this is a diagonal matrix. A diagonal matrix is a matrix that has 0 whenever the row is different from the column. Okay, so what you want to do, you want to look at the square matrix, and you notice that there's kind of like a diagonal right here. This is called the diagonal. First row, first column, second row, second column, third row, third column, fourth row, fourth column. You'll notice that everything that's not on the diagonal is 0. Okay, so this is what's called a diagonal matrix. And the diagonal of this matrix is 1, 2, 3, 4. Now, another important type of matrix is called the identity matrix. So this is a diagonal matrix that has 1 on the diagonal and 0 off of the diagonal. So you can see along the diagonal, first row, first column, second row, second column, third row, third column, fourth row, fourth column. I see that I have all 1s. Now all the entries off the diagonal are 0. Now the identity matrix has a special property that when I take a matrix and I multiply by an identity matrix, I get the original matrix back. All right, so think about like multiplying by the number 1. If I take a number, multiply by 1, I get the original number back. The identity matrix has the same property with matrix multiplication. Now, when I talk about the upper triangle of a matrix, I'm talking about the diagonal and everything above. I didn't do a very good job drawing the triangle on this one. But you remember the 8 and the 0 on there. The upper triangle is the diagonal and everything above it. And it forms a triangle, and it's upper triangular. And these matrices have a lot of special properties. They are, a lot of times they are used in algorithms that are computationally stable. And so they're very valuable to us for like the under the hood computations. In general, as statisticians, we are not going to be getting into these guys directly. Where these are more important is when I'm writing code to do work for me. And I don't actually myself look at the matrix, but I need to be able to tell the computer how to use it to work efficiently. Now, a lower triangle matrix is very similar, but everything, this time it's the diagonal and below are the non-zero entries, and it's 0 above the diagonal. Upper triangle, I have numbers above the diagonal. Lower triangle, I have entries that are lower than the diagonal. The J matrix and the J vector are just special matrices and vectors where they have 1 as every entry. That's it. The J vector is going to be important for representing the intercept in linear regression down the road. Now, 0 matrices are matrices that have 0 everywhere, and the 0 vectors are vectors that have 0 everywhere. That's, we name it that way for a reason. And the notation for the 0 matrix is like a bold 0. And I'm trying to get that a little more clear. I failed. Oh well. All right, so now let's start thinking about like matrix operations. So for matrix operations, the first one we want to talk about is addition and subtraction. So the first thing we have to know when we talk about addition and subtraction is that A and B must have the same dimensions. They must have the same dimensions, otherwise it doesn't matter. Now, if you start working through like different software packages, they'll let you add and subtract in ways that that are incoherent with mathematical addition and subtraction with matrices. For us, they must have the same dimensions. Okay, so A plus B as matrices, I take the entries of A and B, and then I just add them same position. You know, first entry, first row, first column, first row, first column, add them together. Second row, first column, second row, first column, add them together. I just go through and I do addition. Usually students don't have a problem with this. Subtraction, same thing. You know, just take the same position and do subtraction. Now, if A and B have the same dimensions, then A plus B is equal to B plus A, and A plus B transpose is equal to A transpose plus B transpose. Now, the product of a scalar and a matrix. So if I take a scalar, remember a scalar is a regular number. If I multiply a scalar times a matrix, then what I just do, I just take that number and I multiply each entry individually. So I just go through and the first entry multiplied by the number, second entry multiplied by the number, third entry multiplied by the number. I just go all the way through, all the way across. And a scalar times A is equal to A times the same scalar because of the commutative property of real number multiplication. All right, well, that's all I've got for you. I hope you're doing well. Take care and goodbye.